This screencast is about using graphical methods to find the zeros of a function, that is, the solutions to a quadratic function in the form ax squared plus bx plus c equals 0. So let's go over a few vocabulary terms with this. A quadratic equation in standard form gives us that ax squared plus bx plus c and turns it into an equation, setting it equal to 0. Because of that, the solutions to the quadratic equation are called the roots. And the term 0 means the horizontal, or x, in the case of an xy system, intercepts. Now, for a quadratic in standard form, those solutions must occur at the 0 values, at the horizontal intercepts. There could be more than one. There could be up to 2 zeros. So let's try to solve the quadratic equation in standard form, x squared plus 6x plus 8 equals 0 via graphing. We know from a previous screencast that you can find the axis of symmetry by looking at this ax squared plus bx plus c and finding the axis of symmetry at x equals negative b over 2a. In this case, that becomes negative 3. So we know that the parabola, and we also know it's upward facing because the a term is 1. So we know that its axis of symmetry is at negative 3. We also know its y-intercept is at 8. Okay, so we know a lot about this parabola already. So we're going to pick some logical points to the left less than negative 3 and to the right greater than negative 3 in an attempt to graph this and figure out where it's going to hit the x-axis, because where it hits the x-axis are the solutions to this quadratic. So at negative 5, we get a value of 3. When we put in negative 5 and we square it and we add 6 times negative 5, and then we add 8, so in other words, f of negative 5, we wind up with 3. Again, don't forget, when you square a negative number in the real number system, you get a positive number. This becomes 25 minus 30, or negative 5, plus 8 being positive 3. If we do similar things to negative 4, negative 3, negative 2, and negative 1, we get these values here. So the set of points negative 5, 3, negative 4, 0, negative 3, negative 1, negative 2, 0, and negative 1, 3 represent points that we can plot. When we graph these 5 points, and again, the axis of symmetry is right there along this vertical line, x equals negative 3. When we plot these 5 points, we see that we get 0 values at negative 4, 0 and negative 2, 0. In fact, those are the zeros, and they are the solutions to the actual quadratic equation that we started with, x squared plus 6x plus 8 equals 0. So we would say the solutions to the equation are x equals negative 4 and x equals negative 2. And it's always good to go back and double check, make sure negative 4 and negative 2 do make the function equal to 0. In this case, we wind up with 2 real solutions. So the parabola can hit the x-axis, which is the line y equals 0. So with a parabola shape that is formed by a quadratic function, there are really 3 possibilities in it. The most common situation is this middle place where the parabola, whether it's upward or downward facing, hits the x-axis at y equals 0 twice. We call that 2 real solutions. The second possibility is that it hits it once at the vertex. It could either be, all of these can have upward or downward facing brethren. So it can also have 1 real solution and hit the x-axis once, or it can hit the x-axis not at all, in which case it has no real solutions. So again, with these quadratic functions, we have the possibility of 2, 1, or 0 solutions. Let's look at another example. X squared minus 4x equals negative 4. We want to turn that into standard form, so we're going to go ahead and add 4 to both sides using the addition property of equality. When we've done that, we get x squared minus 4x plus 4 equals 0. So we're going to find the axis of symmetry, and that's going to be at x equals negative b over 2a. And since b is negative 4, that's the negative of negative 4 over 2 times a, which is 1. So that's positive 4 over 2. x equals 2 is our axis of symmetry. So we're going to pick numbers to the left of 2 on the number line and to the right of 2 on the number line. So we're going to use 0, 1, 2, 3, and 4 as our 5 points. Putting 0 into this function gives us 4. 0 squared minus 4 times 0 plus 4 is equal to 4. Putting a 1 in gives us 1 squared minus 4x plus 4, it gives us 1. Putting in a 2 gives us a 0, because 2 squared minus 4 times 2 plus 4 is equal to 0. And 3 gives us 1, and 4 gives us 4. We can see that already the function has a 0, turns out, at the actual vertex. When the 0 occurs at the vertex, we have that situation where it has one real solution. Let's take a look at that on the graph. When we go ahead and plot those 5 points, we see the upward facing parabola, which we knew it was because a was positive. And we see that it has a 0, a solution to this equation where this is all equal to 0, at the point 2, 0, which happens to be the vertex. When the vertex is the intercept, it is only going to have one real solution, because the vertex, there can be only one vertex on a quadratic function. Sometimes roots don't occur at exact integer numbers, and in these cases it's good to estimate where they occur. So let's take a look at the quadratic function equation negative x squared plus 4x minus 1 equals 0. So we're going to, again, start with that axis of symmetry, because that's going to kind of tell us where to begin in terms of evaluating points. So negative b, which is negative of b is equal to 4, over 2 times a is negative 1. And so, as in the previous problem actually, we get negative 4 over negative 2, which is positive 2. So our axis of symmetry is at positive 2. We'll go ahead and pick points on either side of positive 2, to the left and to the right on the number line, and evaluate them. Okay, when we do that, we get the following table. At x equals 0, we get negative 1. At x equals 1, our function is 2. At 2, it's 3. At 3, it's 2. At 4, it's negative 1. So the question then becomes, where do the zeros or the roots occur? Well, anytime a function is going from negative to positive, in other words, its value is negative and then it becomes positive, or the reverse occurs, it's positive and then it goes negative. Anytime one of those two situations occurs in a table, as we're going from left to right, then we know that a 0 must occur between those two values. At least one 0. It's possible that many will occur, especially with higher order polynomials. So look and see where this occurs. Well, it occurs between x equals 0 and x equals 1, because at x equals 0, it's negative, and x equals 1, it's positive. So we know there's a 0 somewhere in between 0 and 1, somewhere in that interval. So now we're looking for other situations, maybe where it goes from positive to negative. Well, look here. Between x equals 3 and x equals 4, we have the second situation. The value of the function is positive, then it's negative. Therefore, a 0 or a root must occur, at least one, must occur in here and must occur here. Now, we could actually use a table and get smaller incremental values. For example, maybe we'll go up by 0.1 between these numbers, and then that might allow us to close in on the root. That's one way of numerically solving this. Or we could just graph it and estimate the roots that way. That's what we're going to do here. So when we go ahead and graph that, we can see that the first root is, as we thought, between 0 and 1, closer to 0. And the second root is between 3 and 4, but closer to 4. If we needed more precision, we'd want to use a numeric solution. Let's go ahead and see what that looks like. So if we use a graphing calculator or an online graphing calculator like Desmos here, we can make our table automatically. The first 0 occurs between 0 and 1. So what we would do is, instead of just going up by 1, let's go up by 1/10 and see when we close in on the 0. Okay, so I started at 0 and then I went up by 1/10. And you can see it goes from negative 1 at 0, and then it gets closer and closer to 0. So our 0 occurs somewhere between 0.2 and 0.3. If one decimal place wasn't enough accuracy, then we could even go further. We know it's between 0.2 and 0.3. So we could start at 0.2 and maybe go up by hundredths until we got where we needed to go. Okay, so here we know that the zero occurs between 0.26 and 0.27 because it's going from negative to positive there. If we needed another decimal place, we'd repeat the process. This is what's called a numeric solution. It will eventually get us enough of an accurate answer to satisfy our situation. Approximately 0.27 is where the first zero occurs. Now the other zero, we know it's off over here somewhere. Actually, we can use the graphing portion to almost zoom right in on it, but it's between 3 and 4, but much closer to 4. So let's start at 3.5 and go up by tenths. Okay, so look, going from 3.5 to 4, we knew it was somewhere between about 3.5 and 4. It goes from has an output from 0.75 all the way up to -1, but it crosses that axis between 3.7 and 3.8. If we needed more precision, we could take it to another decimal place and search between 3.7 and 3.8. You can see that this numeric solution is often a time-consuming one. In this screencast, we learned how to find solutions to quadratic functions through graphical methods.